Welcome to the BIMSA Colloquium. Today's speaker is Professor Hiroshi Matano. He was actually my former colleague at the Tokyo University. And he's famous on the analysis of the nonlinear PDs. And so he has several honors, but especially he was the invited speaker of the ICM at the Zurich, so it's 1994. Okay, so today he will talk about front propagation in reaction-diffusion equations and the domain geometry.
Thank you, Professor Funaki, and also other organizers of this colloquium. And I also would like to express my thanks to Beijing Institute of Mathematical Science and Applications for inviting me and giving me an opportunity to speak at the colloquium. So my talk today is on nonlinear diffusion equations, and this is the outline of my talk. I will first explain what reaction diffusion equations are. Some of you may know it already, but other people, there may be some people who may not know what it is. So I will first explain the basic properties of reaction diffusion equations and front motion. So my talk today is focused on the motion of fronts that appear in such equations. So in the second part, I will talk about the front motion in an infinite strip that has a sawtooth boundary, that has a lot of bumps. And in this second talk, it is not for the reaction diffusion equation, but for the curvature-dependent motion of plane curves, which appears as a singular limit of reaction diffusion equations. And my third talk is on front propagation through a perforated wall. So if the wall has many holes, can the front pass through the wall or not? So I will discuss some conditions for propagation and blocking. And it turns out that this third topic we started many years ago, and it turned out that there's a lot of rich mathematics behind this subject. So let me start with the introduction. Reaction diffusion equations and front motion. So this is a typical form of what we call reaction diffusion equations. And so Laplacian U, this represents diffusion, and it is also in physics, it is written more often as nabla squared U. This is the same thing. In mathematics, we use more often this symbol. And f of u, by the way, so the diffusion comes from usually random motion of particles. And f of u is a nonlinear term which describes the growth of the population of the particles. Sometimes it is negative, in which case some particles are removed, and sometimes it is positive. And there are two typical type of nonlinearities that are often discussed. One is the bistable nonlinearity, which has typically this shape, and the 0 and 1 are stable zeros. If you just look at, without the diffusion, if you just look at the ODE, du dt equals f of u, then 0 and 1 are stable zeros. And there's another typical type of nonlinearity, which is the monostable nonlinearity, in which case 0 is unstable and 1 is stable. Both nonlinearities are important, and it appears in different contexts. But in this talk, I'm just focusing on bistable nonlinearities, in which case the front motion involves the curvature effect. So here is just a summary of applications of reaction diffusion equations in different fields of science. The most famous application appeared in population genetics. And in the same year, Fisher and Kolmogorov, Petrovsky, and Piskunov, they published a paper which studied in detail, particularly this, we call it KPP, because this is a very important seminal paper and often cited in many researches. And often we call the equation, in that case, it is this monostable nonlinearity. And they measured how fast the front spreads, which is, so to speak, the quantitative analysis of how mutation spreads within a given population. And then much later, in ecology, Skellan started to use reaction diffusion equations to study the invasion of alien species in a given habitat, particularly in Europe. He was studying the data about the spread of some animal brought from the North America called the muskrat, which was brought to Czechoslovakia in 1905, and it spread all over Europe. And how the territory spread was measured, and it turned out that the area expanded at a certain rate, and square root of area, which is the average radius of the territory, was linearly increasing. And he thought that this can be explained by using reaction diffusion equations and the traveling wave. At that time, he did not know the paper written by KPP, which already gave a very deep analysis of the properties of traveling waves for monostable nonlinearities. Then in material science, Allen and Kahn studied moving phase boundary in a crystal alloy, which I will explain later. And in that case, it was a bistable nonlinearity. And then there are many applications to chemical reactions. In that case, more often it is a system of equations. Also, there is another important application of a nonlinear diffusion equation to a neural pulse model by Hodgkin and Huxley in 1952. And they discovered that a system of reaction diffusion equations and ODE can explain the neural pulse moving at a constant speed without changing its shape. And they received Nobel Prize later in 1963 for this achievement. And also another famous achievement was given by Alan Turing, the famous mathematician who helped decipher German code Enigma during World War II. But he wrote one paper in biology. He killed himself 2 years later, but he wrote just one paper which had a profound effect. From his analysis, it turned out clear that a very complex pattern can appear from a very simple mechanism. And this gave a lot of influence on the development of the idea of self-organization, particularly in 1960s. Prigozhin was influenced by the idea of Turing. And so in his case, it was also a system of reaction diffusion equations. Later in 1970s, people were interested in the stability and domain geometry. So this is the stationary problem for the equation which I gave. And here is a Neumann, zero Neumann boundary condition. So the particles are just reflected. It's a reflection boundary condition. So particles are randomly moving here inside omega, and there is some growth term which may be positive partly and partly negative. So the question was, does there exist a stable solution which is non-constant? So one can easily produce a stable constant solution, which is a stable solution of the ODE without Laplacian. But if you put a Laplacian, things become more complicated, and you can easily construct an example of non-constant stationary solution, but all of them in 1D are unstable. So this was a kind of big open question. And in 1978, and Casta and Holland, and independently myself in 1979, proved that if the domain is convex or an annulus or spherical shell in higher dimensions, there is no non-constant stable solution. Every stable solution is constant. But in the same paper, I also constructed a counterexample. If the domain is dumbbell-shaped like this, and if the neck is very narrow, there can exist a stable non-constant solution, and which I didn't know that it was an open question in mathematical ecology in the United States, and some mathematical ecologists were very much interested in this result, and I got the invitation to become a member of a mathematical Society of Mathematical Ecology in the United States. But I was at that time a student in mathematics. I didn't know what to do with the invitation, so in the end, I didn't accept the invitation. So in mathematical ecology, this means that there is a segregation. There is a region where some species are dominant, and there is another region where another species are dominant. And the boundary is a reflection boundary condition, so it has some neutral effect on the population. And intuitively, it is sort of clear that if the neck is narrow enough, you can construct a stable stationary solution. But you cannot easily construct it by a bifurcation analysis. That's why this kind of domain was not known for a long time. After I discovered this result, about the same time, a new idea appeared. Reaction diffusion equations and mean curvature flow. And this was proposed by Allen and Kahn in 1979, and independently by Kawasaki and Ota in 1982. These are physicists who brought this idea. So let me explain what this means. In the paper of Allen and Kahn in 1979, they were studying the motion of the phase boundary in a crystal alloy. So there are two kinds of atoms. Both has the same density for the black atom and the white atom, but the way they are arrayed are different between here and here. And the area where the white atoms are on the edge and the black atom is at the center, this already has a kind of stability. And the same for the area where the white atom is at the center. So they want to stay like that. So both regions are stable, but because of the random exchanges of atoms, the boundary, phase boundary, moves in time. And they made an approximation by a bistable reaction-diffusion equation, this motion. And then they made a reduction of the motion of this phase boundary to a mean curvature flow, which is this. If this is the phase boundary, the v is the normal velocity. It measures the speed in the normal direction, and h is the mean curvature. N is the space dimension. So n minus 1 times h is the sum of principal curvature. But why does this equation follow from the reaction diffusion equation? So let me explain briefly. But Kawasaki and Ota independently derive the same result, but with a different approach. So intuitive explanation of this is the following. You just express Laplacian on each level surface, S. Then this is the Laplace-Bertrand operator on the level surface, and this is the normal direction. Then, depending on the curvature of the surface, you have to give a correction term. So this is just a change of variable. It applies to any function, any smooth function. So this has nothing to do with the equation. Then, since this surface, on the surface, u is constant, this Laplace-Bertrand part is 0, then you get this equation on the surface. This is, roughly speaking, one-dimensional reaction diffusion equation with a drift term. And this one-dimensional reaction diffusion equation keeps this transition layer stable, while this drift term moves the transition layer. That's how this curvature-dependent motion of the surface comes from. But this is just an intuitive explanation, because this equation holds only on the surface, not outside. But roughly, this gives you an idea. But there is another explanation by using the local energy. And E of u is this integral where w is the minus of the primitive of f. And I assume that, 0 and 1 are both stable. Okay, the position of 1 is actually here. It's a bit wrong. It's here. So it has a local minima. But value at 1 is smaller. So U equals 1 is more stable than 0, U equals 0. In that case, the energy, okay, it is known that this reaction diffusion equations is a gradient flow of this energy in the L2 sense. So the solution of this reaction diffusion equation tries to decrease the energy as efficiently as possible. And what this energy consists of interfacial energy, gradient U, which is more or less localized along the interface, and the bulk potential. There's a difference between the bulk potential near U equals 1 and U equals 0. So this difference gives some sort of pressure. So this U equals 1 area wants to expand it because of the bulk potential difference. And then the interfacial energy, this wants to make the surface area as small as possible. So then we get the mean curvature flow plus driving force. So this is the intuitive rough explanation. And more rigorous understanding of this scenario can be given by introducing some small parameter here. And as epsilon tends to 0, in the singular limit, you get really the interface motion equation. So this is called sharp interface limit. The thickness of the transition layer is known to be proportional to epsilon. And the example is this typical cubic nonlinearity. And in this case, as epsilon tends to 0, you get precisely this. And after the physicists sort of results, many mathematicians worked on the justification of the above scenario from late 1980s to early 2000s. So with this in mind, let's think of the interaction of fronts with obstacles. What is the effect of the obstacle on the front propagation? So here's a numerical simulation of a front motion in the presence of an obstacle, which is a white part. And this numerical simulation was given by a postdoctoral fellow at Kyoto University, Stephen Plunter. As you see, there's a surface tension. Interfacial energy creates surface tension, and it was clear that surface tension appears on the front. So because of that, you can sort of make a guess which direction is faster. So suppose that you have initial data right here or right here. And the undulation, these bumps are non-symmetric. It doesn't have a symmetry between right and left. So here it is gradual opening and a quick closing, gradual opening, quick closing. From this direction, it is a quick opening and a gradual closing. And it turns out that the bigger the opening angles, the slower the speed. And this is because if the front wants to go further from left to right, then here there is a quick opening, so that it has to stretch the length of the interface, which means that you need more energy to increase the size of the front. And so to do that, it takes time. While here, gradual opening, it's okay. The energy supply from the bulk potential is enough to go through, and the quick closing is no problem because the interface shrinks. So this is a typical image which we have to keep in mind. And this, intuitively, this is clear, but in the paper, my joint work with Bendong and Bendong and Nakamura, Ken-ichi Nakamura in 2006 and 2013, we studied this problem rigorously and justified this observation completely. And this is the subject of the second part of my talk. And another observation was given by some French mathematician, by Berestiki, Bouour, and Chapuisat in 2016. If a traveling front, which is coming from infinity through a pipe of constant thickness, suddenly meets an opening. And if the opening angle is too wide, it can be blocked. And whether it is blocked or not depends on the angle. So their result is very much related to what we had for the curvature-dependent motion of curves. Okay, so let's go to the front motion of an infinite strip with sawtooth boundaries. So this is the second part of my talk. So this part is concerned with the curvature-dependent motion of curves in an infinite strip. And this is partly joint work with Bendong, Bendong in Shanghai, and Ken-ichi Nakamura and Ryunosuke Mori at Meiji University. So the problem is the following. So the equation we consider is V equals K plus kappa plus A. In this case, this is two-dimensional, so the curve has just one curvature, which I call kappa. So as before, V is the normal velocity, kappa is the curvature, and the A is a positive constant. And as I mentioned, this equation appears as a singular limit of a reaction-diffusion equation of bistable type with unequal weld depth. And the boundary is not flat, but the boundary is defined by a function of y, g plus and g minus, which depend on epsilon. And epsilon, g epsilon plus minus is epsilon times g plus minus of y over epsilon, which means that as epsilon tends to 0, the shape of the boundary doesn't change, but the size becomes smaller and smaller. I put epsilon here because I wanted to study the homogenization limit as epsilon tends to 0. In the homogenization limit, it becomes flat. So you don't see the bumps anymore, but there is a tiny micro-local bumps which affects the behavior of the curve here. So the motivation is to study the effect of geometry on the speed of propagation and also on blocking. In some cases, the motion of the curves is blocked. So there is an important quantity, which I define here. Alpha plus minus is the maximum opening angle. As I mentioned, this is the opening angle. The front goes from bottom to top, upward. So alpha is the opening angle, and beta is closing angle. And in our earlier paper in 2006 and 2013, we assumed the boundary slope condition at that time. So the opening angles, maximum opening angles and closing angles are less than pi over 4, 45 degrees. And then one can show that no singularity appears on the curve. So we can work on the problem in a classical category. So the solution is all differentiable, and it satisfies some certain quasi-linear partial differential equations. And we gave several results, but among other things, in the paper in 2006, we considered the homogenization limit. Okay, under the condition that G plus minus is periodic, so it has periodic boundary conditions, periodic in Y, and the boundary slope conditions. So the angles are less than pi over 4, so no singularity. And we studied the limit as epsilon tends to 0. Then formally the boundaries become a straight line in the limit. So you don't see the bumps, but there's a tiny bump, which is felt by the curves near the boundary. So in the limit, what is the shape of the curve and what is the speed was the question. And we showed that the limit speed depends on the maximum opening angle, alpha plus minus, and no other geometric features of the boundary plays a role. So this was a surprising fact even for us. Only the maximum opening angle determines the speed in the homogenization limit. And this result also shows that rigorously that the bigger the maximum opening angles, the slower the speed. So we proved this sort of observation rigorously. And the way we proved it, okay, here as you see, here the direction angle of the end points of the curve changes very, very quickly. The distance between the bumps are epsilon, so as the curve goes up, it changes very, very quickly. So that at first we didn't know how to estimate this. Then it turned out that if you estimate the angle of the curve at a distance which is square root epsilon away from the boundary, then we found that it stabilizes, the shape stabilizes. Beyond that, if you are too close to the boundary, it is so wild motion, and you don't see anything. So quick changes of angles. But here, it stabilizes. But if you are further away from the boundary, you don't really get enough information of the boundary. So square root of epsilon, we found, was precisely the right distance from the boundary. And this is how we were able to determine the speed in the homogenization limit. Okay, in the paper in 2013, we considered a different situation. And again, the boundary slope condition to avoid singularities. And the boundary is no longer periodic. We wanted to study non-periodic boundary conditions. And in that case, fluctuation of the propagation speed can occur. If it is only, okay, if it is strictly ergodic, or still in this case, the non-periodic case, this can happen. Minimal speed and maximum speed. You just take average of the speed on a long time interval, but depending on where you measure, the speed may change. It fluctuates. Oops. By the way, let me just explain various. Oops. Okay, so okay, maybe this is okay. This is the one. So I consider that, okay, just let me explain various classes of heterogeneity. So g of x is a function, actually any function which is uniformly continuous and bounded. And sigma s is a shift operator. Then you define a hull of a function like this. Okay. Okay, G is not necessarily uniformly continuous. If it is uniformly continuous, this hull can be taken by L infinity on R. If it is not, if it is just bounded and continuous, then this hull is taken in the local uniform convergence topology. Then, depending on the structure of the hull, the type of the heterogeneity can be characterized. If it is periodic, then Hg is homeomorphic to a circle S1. So the shift of G just goes around the circle. And if it is quasi-periodic, then hull is homeomorphic to a finite dimension torus. And the shift of G goes around this torus densely. And almost periodic class is when the hull of G is compact in L-infinity. And the recurrent case, it is compact in L-infinity local, and moreover, every orbit is dense. And there is a class between almost periodic and recurrent, which is strictly ergodic, which is uniquely ergodic and recurrent. So we studied the motion of the curve when the boundary is strictly ergodic. And by the way, this is how we can construct a strictly ergodic function. Just an example. So these are two parallel lines which has irrational slope. And you just go within the two parallel lines as much as you can horizontally, and if you cannot go further, you go up, and you repeat this procedure. Then this array of A and B, A is vertical motion and B is horizontal. Then this is, you create a continuous function depending on this array of alphabets. Then you get a strictly ergodic function. So this is certainly not periodic, but it is even not almost periodic. Almost periodic is a too strong condition. This belongs to a wider class. And then what we found is that well-defined propagation speed. If C minimum is positive, actually, C min and C max are equal. So the propagation speed is well-defined. But there's also a possibility of, there's also a possibility of C min being equal to 0 while C max is positive. We call it virtual pinning. In that case, the front moves upward to infinity, but average speed is 0 because C min dominates. If it is, there is a time when it is very, very slow, then the total average is 0. So 0 average moving propagation speed, but it still propagates. So we found this kind of things. And what does it mean? So if this is the halo of omega, the shift of omega forms a trajectory which is dense in the hull. And there is a blocking stationary solution somewhere on the hull, but the actual trajectory omega doesn't hit this. So in that case, you never see along omega any blocking stationary solution, but you come as close to this blocking solution infinitely many times. That slows down the speed very much. So we studied this kind of things in 2013. Then more recently, this ongoing work with Ryunosuke Mori, we removed this boundary slope condition, periodic but non-boundary slope condition. In that case, singularities form. The curve, this is the end point of the curve, which we assume that it is perpendicular to the boundary of omega. Then the curve may hit the bump of the boundary in the middle, then it splits. And so we studied this kind of motion, and it turned out that by allowing the curve to create singularities, a new phenomenon, which we call obstacle-aided propagation, is discovered, which I will mention shortly. Here is a numerical simulation. If you have a single bump, it is stopped here. It is narrow enough to stop the motion, but if you have many bumps which are close to each other, then it doesn't stop because it will touch the upper bump before it completely stops. So, and we also showed that the denser, the closer the adjacent bumps are, the faster the speed. We also proved it. So this is again a simulation by Stephen Plunder of Kyoto University. So, and by the way, which direction is faster? As I mentioned, the bigger the opening angle, the slower the speed. So this is another numerical simulation. By the way, this is a bit close to this tower. And so let's see. From bottom to up, there is a quick opening angle. From top to bottom, the closing angle is quick, but opening angle is slow. And certainly, this sort of verifies what I said. Okay. Now, let me go quickly to the third part. Front propagation through a perforated wall. So this is a completely different but related problem. This is a condition for propagation and blocking. And this is joint work with Henri Beresticki of EHESS Paris and François Hamel of Aix-Marseille. And so I consider bistable reaction-diffusion equation. And this is unbalanced, so it has the corresponding potential function W has two local minima, 0 and 1, and this condition means that u equals 1 has a lower energy, lower potential. And then there is a traveling wave, and using this traveling wave for 1D, one can consider traveling planar wave, or you can call it plane wave, which has this kind of shape. So it is flat, it has a flat boundary. The question is what happens if there is an obstacle? Can it pass through the this obstacle or not? So that was the main question. Okay, oh, sorry, something went wrong, I don't know. Okay. Then this is the description of the obstacle. The obstacle has finite thickness, and it is connected. And for some results, we also assume that it is periodic in Y, for some results. But for other results, we don't. And periodic in Y means that there is independent vectors in the Y direction, such that the shift of the wall K to these directions makes K invariant. So this is a typical image of a wall with periodicity. So under what conditions can the front pass through the wall is the main question, and I will give you another numerical simulation. And if the holes are small, it is blocked. So intuitively, it is clear. But the question is how to justify this observation theoretically. And it turns out that there's a lot of rich mathematics behind this question. And to study this problem, I defined a limit profile. This is the front solution, which approaches from infinity towards the wall. And it is known that this U bar, this front solution, is a monotone increasing in T, so there is a limit. And we call it the limit profile, and the shape of the limit profile tells you whether the front managed to pass through the wall or not. And this V bar satisfies this stationary problem. And it is anyway stable. And we define propagation if V bar goes to infinity beyond the wall, goes to 1 beyond the wall. And we call it blocking if V bar goes to 0 beyond the wall. So these are typical images of V bar when the propagation occurs and when blocking occurs. So the question is whether which is the case, to study which is the case. But first, we had to show that no other situation occurs, either propagation or blocking. And this is what we call dichotomy theorem. And V bar goes to either 1 or 0. And moreover, this is an important part, uniformly, regardless of the choice of K, which we proved by using Liouville type theorem on Rn. And so which means that if blocking occurs, V bar doesn't go to 0 far away from the wall. It has to go to 0 already in a neighborhood of the wall. And an important implication, okay, idea of the proof is a limiting argument and Liouville type theorem, but important, okay, this is the important corollary is the following. If there is a sequence of walls which blocks, the limit wall is the limit in the Hausdorff distance is also a blocking wall. Okay, I don't think I have time to explain this corollary in detail, but roughly speaking, the family of blocking walls form a closed set, while that of non-blocking walls form an open set. And this is an extremely useful observation for later arguments. And sufficient condition for blocking, we studied blocking occurs if the holes are narrow enough. This is natural. And we proved it by constructing an upper barrier by variational methods. And in order to make the variational method to work, we had to define some local energy. And because of that, we needed to assume that either the holes are localized in a bounded area, in which case we can just define the energy around the hole, or the holes are arrayed periodically. So even if there are infinitely many holes, they are all periodic. So again, we can define energy which is periodic. So both works. So far, if the holes are arrayed non-periodically, the question is open. And then lastly, we studied the sufficient condition for propagation. And there are three cases. Wall with large holes, which is natural. But a more interesting case is the small capacity wall and the parallel blade wall, which I will explain what they are. The wall with the large holes is when there is a hole which allows a ball of a certain radius. There is a critical radius R0 that allows the ball of this radius to go through. If there is even a single hole on the wall, then the entire front can penetrate into the other side of the wall. And the small capacity wall is that there may be no large holes, but if the wall itself has small capacity, more precisely, K is close to a set of capacity 0 in Hausdorff distance, then propagation occurs. And the third one is parallel blade wall, when the walls look like very thin panels that are parallel to the x1 axis. X1 axis is the direction of the propagation. Then it is also true. This has one codimension. So the capacity is not small. For the capacity to be close to 0, it has to be close to at least 2 codimensional set. So the case C has to be taken care of completely differently from case B. And the method for the first case is just comparison principle and the sweeping argument by lower barrier. And case B, the limiting argument and the removal of singularity and dichotomy theorem, which corollary to, by corollary to, by which I mean that the limit of blocking walls is again blocking. Using this corollary and removal of singularity theory, one can derive a contradiction if the blocking occurs for a very small capacity wall. And the last one is another method using relative Poincare inequality, which I will explain shortly. So this is a small capacity wall. It doesn't need to be has a small capacity. Suppose that there is a hole which has a large enough interior radius. So Then you fill the hole with a debris of small capacity. If propagation occurs in A, then also propagation occurs for B if the debris has very small capacity. And this can be shown by, as I said, the limiting argument and removal similarity theory and dichotomy theorem. And the interpretation of the result is that since the front has positive thickness, it is not very sensitive to debris of small capacity. So this is the difference from the singular limit, sharp interface limit case in which the front has a thickness 0 and moves by motion by mean curvature plus driving force. So this is this result holds only if the front has a positive thickness. And the parallel blade wall is something like that, but let me just mention that it is not just kind of this kind of panel, but also honeycomb wall is also an example. And definitely the capacity is not small, but if it is parallel and very thin, it works. And as I mentioned, relative Poincare inequality works. And okay, let me just skip this argument. But the relative Poincare inequality, by which I mean that if you have a large domain and subdomain D, and there is a function which is H1 and continuous, and 0 on the boundary of D in the interior of omega hat, but no boundary conditions specified when the boundary of D touches the boundary omega hat, then you get this inequality. This is a generalization in some sense of Poincare inequality. In the case of standard Poincare inequality, you assume that W is 0 on the whole of boundary D, but here we are assuming that W is 0 only on a portion of the boundary of D. Okay, so this is the summary of my talk. This is the first part is motion on plane curves in an infinite strip, and we gave an example of obstacle-aided propagation. I gave you, just showed you a numerical simulation, but we also proved rigorously that this can happen. And for front propagation through a perforated wall, we showed that the family of blocking walls form a closed set, and that of non-blocking set form an open set. And this is very, very useful for deriving sufficient condition for propagation particularly. I think I should stop here, and thank you very much for your attention.
Questions? Are there any questions or comments? Yeah.
When you discuss the propagation of the front through the perforated wall, what will happen if you will consider, for instance, the specific particle which has a biased diffusion and tries to penetrate through the perforated wall? Will you have some changes, or if you have some kind of discreteness in the system?
Okay, so in that case, of course, it's a good question, and to be honest, I haven't studied this problem yet. Of course, in this case, some particles can annihilate. If the density is too small, some particle just disappears, but the density is close to 1, more particle is created. So it's not just a mass conserving case, but still the discrete version of this problem would be very interesting. Thank you for your question. But this will be a future work, or if anyone has a new idea to study this question. I think this is a very good question, but so far this is beyond our reach.
Any other? Okay. So maybe I ask only one. Okay. Short question. Okay. So you proved the dichotomy of the last problem.
Yes.
When K is periodic.
Yes.
So if not periodic,
no, dichotomy holds for any K.
For any K.
Any K. I assume the periodicity only for two cases. One is blocking. Blocking, either the holes are localized in a bounded region or periodic, and the second one is parallel blade, like honeycomb structure, because again we use some sort of integral, and it has to be in a finite, either bounded region or periodic. But dichotomy theorem holds for any case. It's a very general theorem. Yes.
So it is blocked, then it's totally blocked. You cannot go any from some faraway place.
So as a corollary to the dichotomy theorem, the family of blocking walls form a closed set. So the limit of blocking walls is again blocking. And this is very, very useful in studying the wall with a small capacity. So if you just add some debris of small capacity, if the capacity is small enough, you can show that it is non-blocking.
Okay, so I am also interested in the random case. So in the first part, maybe the second part, you are talking the some ergodic, strictly ergodic case, but
yeah, ergodic one is for the this first problem, but the second problem, it is still open question if the holes are narrow but distributed randomly. So intuitively, it should block the propagation, but we were able to prove it rigorously only for the periodic case and the bounded case, because we needed to define an energy function to construct upper barrier. Yeah.
Okay, thank you very much. So, are there any further questions or comments? If not, maybe let's thank the Professor Matano. Thank you very much.
Thank you very much.